Hey, Ta. Just plug something in here and get started. I'm glad I'm recording today because it looks like a lot of you are going to be getting this content over Zoom instead of in person here today. So, um, let me first of all, basically today we're going to be covering chapter five and pretty much all of chapter five, where we talk about continuous random variables. We've been talking about discrete random variables up until now, where you had those probability distribution tables that you were doing, and you also had the binomial distribution. But all these probability distributions so far have been showing up as bar graphs. Here today, we're going to move beyond bar graphs to basically a line graph that draws a curve that describes the probabilistic nature, not of discrete numeric quantities, but of continuous numeric quantities here. So we're going to actually which the most well-known example of this would be the bell curve. Before I do that, let's first of all take a look here at where we're at here in the summer. I've got some for this that are due basically a week from today, and that'll uh, take care of all of chapter five there. There's a test a week from this Thursday that'll be chapters four and five combined. Since there's such short chapters that, it's appropriate to combine them like that. We also have project four, which I actually moved this to a week from today here so that you'd have a little extra time with that here. That's going to be another watch the video and put something on your spreadsheet type of project. So, and I'll just be going through and checking that pretty easily. I've printed off all of your project threes here. They look, pretty cool. I'll also be handing back some tests here today, so that we can talk about those as well here. Hey, okay. We do not have class on Thursday. This is our only class for this week. So we'll come back a week from today. Okay. And there's really just one concept that you need to get from this section here. If you get nothing else, it is this. What in the world does that mean? Well, you'll find out, and you'll know by the end of this period here why that's suddenly cutting out on me. Shouldn't be. Plug it back in. Okay, that seemed to help. Um, so really just the big thing that the step we're taking from the previous chapter here is we've introduced this whole thing called probability distributions here, which is the way we describe the behavior of a random variable. But all of our probability distributions thus far have been with discrete values of that random variable. If you recall, they would be heads or tails, spades, hearts, clubs, or diamonds. They would have been, a two or a three. They would have been numbers of sixes that you get. In other words, just discrete values here, never fractions, never decimals. But in going from the previous chapter to this one here, we're going to switch to continuous numeric variables that are not bar graphs anymore. They're smooth curves. And the transition is going to start here with this distribution here, which may look somewhat familiar here. If I'm rolling a single die, what are all my probabilities for getting a 1, a 2, a 3, a 4, a 5, and a 6? And the answer is 1/6 for each one of these, 1 and 6, right? And so we actually call that a uniform distribution because it's really the same value for each one of these possibilities here that we see, 1 through 6. And there's one thing I want you to start to see here. What is the area of a rectangle? How do I find the area of the rectangle? Length times width. Okay, so if I'm laying down carpet into this classroom here and we assume that it's perfectly rectangular, it's got a little portion knocked out of it here in one corner. But if we treat it like a great big rectangle, how do we figure out the square footage in this room if we're laying down carpet? Same thing. So what do we do? Yeah. So what would that look like? We take a tape measure and do what? Measure two sides. These two sides? No. Okay. This side and this side multiplied together, we get the square footage in here. So very, very good. So length times width is area. So let me ask you a question here. If I assume that the width of this rectangle is just 1, and that this one is also 1, and this one's also 1, 1, 1, and 1, and this here is the decimal version of 1/6. So this goes from 0 to 1/6 here. What's the area of this first rectangle? I've got 1 times,
Oh,
which is
what?
1/6. How about the second one? Same thing. So notice that the area of each one of these rectangles is the same thing as the probability values for each one of these. That's easy because each one of these rectangles has a width of 1. Starting to set that concept up for each one of you. Area and probability are the same. And we can see that here as well. All right, so if I assume the width of each one of these rectangles is 1, and the height of each one of these is the probability, well, this is the probability of 2, the area of this is the probability of 3, and so on. And all of these probabilities are going to add up to 1. But the important thing is that the area of this rectangle is the same thing as the probability. Okay, so let me take you to a less discrete kind of problem here. Let's say that this clock on this opposite wall over here, it's a face clock, not a digital clock over here. It's running on a battery, and that battery is going to run out. And let's take a look at the minute hand on that one. The minute hand on this one is between the 11 and the 12. The minute hand on that one is between the 5 and the 6. It's going to stop somewhere around the clock. So what is the probability that when this battery conks out, that this hand here will stop somewhere between 2 and 5? What's the probability there? So here's one thing that you mentioned. It's going to be out of 12. Okay. So it sounds like, Ty, you have divided this up into a bunch of sections. In particular, how many sections? 12 sections. And how many of those sections are members of the event? 2 to 5. 3. And how can I reduce that? 1/4. Now, let me do this here, and you'll kind of start to see a little bit more. If I spin a spinner, what are my chances of spinning somewhere in there? Well, there's 4 equal sections here, as you can see, and this is one of the 4 sections. So you can see it that way as well. See that? What's up?
Is that gonna be a right angle triangle? Like the,
Yeah, this is a right angle, isn't it? Yeah. So, a couple of different ways to see that. But how did you get the 3 here? Let me ask you. How'd you get the 3 there, Tom? Okay. If I were just looking at these numbers, how did you get the 3? Okay. Or another way of saying that, 5 minus 2 is 3. Yeah. And you mentioned that there were 12 sections here with this. If we think of this as starting at 0 and then going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 on the end there. We've got 12 separate sections here. Now, let me ask you, as this thing is moving around the clock here, is there any reason why it would prefer stopping over here versus over here versus over here? Or is it just pretty much random where it's going to stop? I mean, the battery's running out. Do we have any reason to think that it'll prefer one side or the other where it stops? No. Up, down, left, right. So what does this probability distribution look like here? If I'm starting here and this is 0, it's really where 12 is. 1, 2, 3, 4, 5, 6, 7, 8, 9. And of course, I don't have enough room. 12. So, what would you expect this distribution of probabilities to look like? Is it different in some places or is it the same everywhere? The same everywhere. This is a uniform probability distribution. And is it possible for this thing to stop somewhere not exactly on 1 and not exactly on 2, but somewhere in between 1 and 2? Is that possible? And in fact, you might even suggest, look up here for a sec, what is the probability that it stops exactly on 2? Exactly on 2. What's that?
1/6?
Yeah, if it's stopping exactly on the 2. I mean, not over here and not over here, but stopping exactly on the 2. Sorry, that's where my head is. I mean, we're not talking about a 12th of the pie anymore, are we? We're really zooming in now on whether or not it's going to land on the 2. And maybe we get close, but then I get a microscope and we zoom in all of the more, and we have a great big 2 here, and oh, we discover that slightly below the 2 or slightly above the 2. Or maybe it's not. Maybe it's right on the 2, but I zoom in a little bit more with a more powerful telescope here.
Maybe 1.
A 1 probability? That means 100%. So yeah, what's the probability that I'm going to hit exactly 2?
It's
So here's another way of saying it. Let's say that I am throwing darts at a board. What is my probability of getting an exact bullseye? So why do you say 50-50?
It's
Okay. So yeah, it's a possibility that it might be in this larger circle. There's a possibility it might be in this little circle here. But how big is this point here? Doesn't have any size to it. Is it more likely that it's going to hit in this large section or more likely it's going to hit in this section? The large section. Why? Because it's a more amount of real estate there, isn't there? And so the smaller the area here, the less the probability that I'm going to hit it, right? Yes? We good? Less probability? Okay. And let's see, I asked, how big is this point here? And you said, but yeah, how tiny? You said it. Yeah, but how small?
very
How
small.
big is a point? Zero in size, right? The center of this room, if you want to know exactly where the center of this room is, it's going to be some point, and it's going to be zero in size, right? If I nudge off of that even the slightest microscopic amount, I'm off center. If we're wanting to be absolutely exact, then we're dealing with a point, a location of no size. Does that make sense? In the same way, what are the chances that this hand lands exactly on two? Not above, not below, but exactly on two. That probability is also zero.
So it's saying it's a 0% chance that it can do.
Yes, there's a 0% chance that it's going to hit exactly on the two. And the important word there is exactly. That's very different from what we had in the binomial distribution, wasn't it? We were always dealing with probability that x equals 2 and probability that x equals 4 and stuff like that. Whenever you're dealing in a continuous distribution here, the probability that x equals anything is always 0. We can only talk about questions like what's the probability that it lands somewhere between 2 and 3? And that was your 1/12th. That was one of the 12 pies, wasn't it? See that? And so, yeah, from 2 to 5 here, what is the probability that it lands somewhere between, let's say, 1 and 2? How many pieces of the pie is that? Between 1 and 2?
One?
One of the 12 pieces. So yeah, this probability here is 1/12 between 1 and 2 here. And the probability that's in between 12 and 1 is also 1/12. And the probability that's between 6 and 7 is also 1/12. So this is a uniform distribution just like before. And what's the distance from 1 to 2 in this x direction? This is just 1. The width of this rectangle is 1. So the area of this rectangle is 1/12. And the area of this rectangle is 1/12. And so on. and so on and so on and so on. Here's another way of seeing this. What is the width of this entire rectangle? 12. And the area underneath the whole probability distribution has to be what? The area under the whole probability distribution always has to be 1, because all the probabilities have to add up to 1. The area underneath this thing, total area, equals 1. Always, always, always. And so if the width of this rectangle is 12, and the area of the whole thing has to be equal to 1, then what does the height of this rectangle have to be? 1/12, because 12 times 1/12 is equal to 1. Does that make sense? Ooh, not sure I'm getting through. So in this instance, we're dealing with a continuous probability distribution here because we're allowing ourselves to ask the question, what is the probability that it lands somewhere between 6 and 7? Well, that's the difference between these two. It's 1/12. Okay, so that's this right in here. Okay. And we're finding that when we do that, we're dealing with a probability distribution here that has some of the same properties that we had for discrete probability distributions, but this is a smooth line instead of a series of bars. And what do we find for this shaded area here? This is 3/12 or 1/4 for each one of them. And actually, can you see that from taking a look at the dimensions of this rectangle here? The height of the rectangle is 1/12, and what's the width of this rectangle? 3. And so 3 times 1/12 is 3/12. Okay, so we'll do a lot of problems that are like this here. So we'll get a lot of practice with this. Is it all right if I erase this here now? I'm not hearing any objections. So you can see here, we're now dealing with a uniform probability distribution. This is the location where it stops, where this hand stops. And this is our probability value going across here. 1/12 everywhere. There's an equal probability that the minute hand will stop anywhere on the dial. So we have a flat distribution. And again, the total area under the distribution is 1. So the total area of this blue rectangle is 1, which also makes sense because it has a height of 1/12 and a width of 12. 12 times 1/12 equals 1. Okay, so if we want to ask the question, what's the probability that it lands somewhere in between the 2 and the 5? Now we're asking the question, what is the area of this shaded rectangle right in here? And it's just like finding the same thing for the larger rectangle here. The width of this is 3. The height is still 1/12. This is 3/12 or 1/4. Notice probability and area are the same thing. Excuse me. Okay, so what if we describe the position of the minute in terms of degrees clockwise from 12 o'clock? So this is, see around the circle here, this would be 30 degrees, 60 degrees, 90 degrees, 120 degrees, 150, 180. This goes all the way around. Eventually it's 360 to go all the way around. Okay, so if that's the case, then we're measuring this in terms of degrees. What is the width of this rectangle here now on this scale? Not 12 anymore. It's 360, which means in order for the area of this rectangle to be 1, the height of the rectangle is no longer 1/12, it is 1 over 360. And again, we would figure out the area. Um, we would figure out the probability of it landing somewhere in between this angle and this angle by finding the area of the shaded rectangle here. Okay, kind of hinted at this type of thing before here. Um, if we have a dartboard, how do we generate a probability distribution for the distance that we are from the bullseye? Let's see here. Let me draw my, let's say this is right at the bullseye, and this is, let's say, 12 inches from the bullseye. Which is higher, 12 inches or zero? Which is more likely? 12, yeah. What's the probability that we found that it hits an exact bullseye? Zero. And so I don't know if it goes up. We might say something like this. It's probably a quadratic just because pi r squared. So it goes up like that. Um, but probably the most important thing is the probability of hitting the exact center is zero. Um, think about this. How would we generate a probability distribution for the lifespan of a light bulb? First of all, what kind of light bulb do we want to choose here? LEDs or incandescent? LEDs? Okay. How long do LED bulbs last? 10 years? Somebody said 15 years? Okay. What would be the maybe the shortest time span that they would last? 2 years? Okay. Somebody said it most likely around 10 to 15 years, you said? Okay. What's the maximum amount of time they might last? 50 years? Okay. So let's see. 10, 20, 30, 40, 50, 60. So this is 10, 20, 30, 40, 50, 60. And oh, this is zero over here. So this is probability. This is in years. Lucy, I think you said that it would, at the very, very least, it would last like 2 years. So there's no chance it's going to last less than 2 years. And I think, Ta, you said 50 years for a maximum. So there's no way it's going to last longer than 50 years. And I think you said 10 or 15 years be the most likely. I mean, we're just theorizing here very much. I don't really know. But that tells me that our probability distribution might look, what do you think? Something like that? If the lifespan of every one of our LED light bulbs fits somewhere in that curve, with the most likely values being somewhere between 10 and 15 years, but all of them being somewhere between 2 and 50. Are we dealing here with a discrete variable or a continuous variable? Discrete or continuous? In what way?
Because after years, it's
Okay, well, that's true. But if we were to take a look at all of the data coming in for each one of the light bulbs, would all of the data be in whole numbers or could it be in whole numbers with decimals? Possibly. But is it possible that it could be whole numbers with decimals? Could somebody say this lasted 4.6 years? Yeah. So it's possible that we could have, really, really accurate values here. And so is this a bar graph or is this a line graph? It's a line. Okay. And in fact, it's possible that, if we really knew, I mean, maybe it's crazy, something like that. Hopefully not bending back like this, but, you know, but, uh, you know, very, very complex function like that. Okay. Area under the probability distribution is probability. And we always have to have the area in between two values. So if I go back here to this, maybe I can get rid of the uglier one here. How would I find the probability that it lasts in between 15 and 20 years? I slice it here and I slice it here and I find the area in between these two values. And if I can find this area, then I know the probability that it's going to last between 15 and 20 years. With that in mind, what is the probability that it's going to last exactly 10 years? How far apart are my two knives? Yeah, they're right on the same spot, aren't they? So my slice has zero width. And what's the area of a rectangle with zero width? It's zero. Exactly. So the probability that it lasts exactly 10 years down to the femtosecond, the microsecond, the millisecond, the probability of that happening, we're going to say is zero. Okay, so the key word there is exactly. So when we're dealing with continuous distributions, it's always the probability of x being in between two things here. And so we have this is called a compound inequality. And this is the way we say mathematically that x is in between two numbers. Two less than signs allows us to say that. So the direct translation of that is 15 is less than x, which is also less than 20. Okay. So yeah, you're going to be working with different probability distributions in which you're having to slice them like this. You're going to be slicing normal distributions and t-distributions, um, pretty much for the rest of the summer here. So, what's the probability that whatever this thing is describing, what's the probability you're going to get an answer somewhere between one and looks like three, one and three here? It's going to be whatever the area of this blue mass is. So all this stuff is still true even when we're not dealing with rectangles. And again, what's the area under this entire curve? Kind of a strange question. Area under the curve. But since it's a probability distribution, what is the area under the full curve? It's got to be what? What? Exactly right. Always, always, always. Okay. And what's this probability that x equals 3? 0. That's 1 there. Okay, so that's the extent of concepts there for that first section.
So the area for the shaded area, or shaded area.
Yeah, for this chapter, I won't ask you to do any of that stuff for anything other than rectangles.
Oh,
Yeah,
I was going to do the
yeah.
second part.
But eventually, we're going to be doing the same thing, but for the normal distribution, and you actually need to have something on your spreadsheet to be able to calculate that for you. And we might actually have some time to go through that process of putting that together here. In fact, that might be a good idea for us to do that. Okay, what was I going to do? Oh, yes. Okay, so the simplest continuous probability distribution that we have is the uniform distribution. We've been dealing with this already, a lot of these here. So we're going to be calculating things like the mean of the distribution and the standard deviation of it and all that sort of stuff. We could do that with the binomial distribution and all those discrete probability distributions from the previous two chapters. We can do the same thing with continuous probability distributions now. Okay, so I'm showing here some data. I don't recall if this is good data or false data here, but they're smiling times in seconds for a 2-month-old baby. How long does the baby smile for in seconds? 10.4 seconds, 5.8 seconds. If you were to put these numbers into your spreadsheet, you would get an average of 11.49 seconds with a standard deviation of 6.23 seconds. Okay. Let's assume that these data come from a uniform distribution extending from 0 to 24 seconds. Then in reality, if you looked at all babies, it would be a distribution, a uniform distribution going from 0 to 24 seconds here. If that's the case, what's the width of this rectangle? Close. 24? Yeah. And remember, what's the area under this rectangle here?
What?
1. And so what does the height of this rectangle have to be? Because 24 times whatever this is has to be equal to 1. 1/24th. I like it. Yeah. And so this line here, I know it's a line, but it's actually a function. We describe this probability function here as just being this constant, 1/24th. There's no x squared or anything like that because it's constant. We don't need to put x in there at all. But that's our function. And so the way we describe this, you've seen this before when we were dealing with the binomial distribution. We had, if we assume that x is the result of a binomial experiment, it's from a binomial distribution with this number of trials and this probability in here. So this is basically what this tilde means here is that the numbers that we're getting here are coming out of a distribution that looks like this. Okay. And this is the notation that we use here for saying that our data values x are distributed as a uniform distribution going from 0 to 24. So this is the minimum and this is the maximum. So you're learning how to talk like a statistician just by using this funny little symbol here. Just means that it's distributed that way. There's actually only one other example of this, and that's a normal distribution. So and you'll see it with those parameters there at some point. That's coming up. But so it's those three distributions here that you're going to see at some point. Okay, so where do you think the mean would be for this distribution here?
Well,
Yeah, why is it 12?
because they're
Yeah, because it's in the middle here. Yeah, I remember if you recall, if you were a waiter, a server someplace, and you were balancing this distribution on the tip of a finger, where would you have to put your finger in order to keep everything in balance? Well, it'd be right here in the middle at the 12. It's easy when it's a uniform. If I've got more on one side than the other, then it gets a little harder, doesn't it? Okay. But that's what the mean is. That's another way of seeing what the mean is. Median and mode are different, but that's a good way of understanding the mean. And yeah, we get that by taking this number and this number, adding them together and dividing by 2, finding the average of those two numbers there. So if I call this A and this B, then what is my formula here for finding the mean of this distribution?
A plus B over two.
A plus B over 2. So yeah, the mean of a uniform distribution comes from that formula. And with that in mind, how do I figure out what this function is right in here? Well, how did we do it before when it was 0 to 24 here? What was this distance? 24. And then we did what to figure out what this function? It was 1 over that. So if I'm switching now to these variables right in here, how do I find the distance from here to here? What's the mathematical thing that you had to do? It was 24 minus 0. So now it's going to be B minus A. B minus A, which means that our function here is going to be 1 over B minus A. So we call this the probability density function for a generalized uniform distribution going from A to B. Okay, so now we have two formulas for this. And we also have the variance and standard deviation formula here. The variance here is B minus A squared over 12, believe it or not. And we can find the standard deviation just by taking the square root of that. So those are our four equations to describe this uniform continuous probability distribution. Yeah, I added another one there for variance, but you know. Okay, so how would you calculate the probability that the baby smiles for less than 8 seconds? Less than 8 seconds. So that's, how would we say that? Here's my, uh, how would we say that? That's the probability that X is less than 8. So recall the distributions going from here, 0 to 24. So what's the height of this thing again? Help me out with that. 1 over the whole thing. 1 over 24, yeah. So that's still going to be the height of this rectangle, isn't it? Right. But what's the width of this rectangle here? This is 8, isn't it? So what's the area? We don't need our calculators for that. 8 out of 24, yeah. And actually, we can reduce that because 8 goes into 24 how many times? 3 times. So this is a 1 in 3 chance that when a baby is smiling, that smile is going to be lasting less than 8 seconds, according to this distribution right in here. Does it make sense how we did this here? Okay. Mm-hmm. Mm-hmm. But let's also expand this out here to get a nice little general formula. How did we get this 1/24th here if we're just looking at A's and B's? This 1/24th was 1 over B minus A, right? So that's where that came from. Where did the 8 come from? Let's label this as let's label this as B, and B and A are the same thing here. And I'll label that as C. Where did the 8 come from?
Um,
8 minus 0, right? So in this case, it's C minus B, or C minus A in the case here. But so this was C minus B. And so we have a general formula here. Oh, oh, sorry, this should be C and D. My goodness. So that's D minus C. I repeated B twice here. Didn't want to do that. So this is good grief. C to D. So it is D minus C over B minus A. Let me rewrite that. D minus C over B minus A. So how do I find the probability that a baby smiles somewhere from 10 to 15 seconds? My A and my B are still the same, but my C and my D are here and here. So what's my probability that the baby's smile lasts somewhere between 10 and 15 seconds? Well, here's my formula. D minus C, that's 15 minus 10 over B minus A, that's still 24 minus 0, isn't it? So I get 5 on top and 24 on the bottom. So just a little under little over 20%. Okay, so we have another formula in our pantheon here. Formula for finding the probability that we're in some portion of this distribution here. Okay. What's the probability that the baby smiles for more than 15 seconds? So just fill in what you know. It's something that you know here. What's this point out here? 0. A is 0. What's B? 24. What's C? C is 15. And what's D? Also 24. Yeah. So A spans the whole rectangles. A and B span the whole rectangle. C and D span just the shaded rectangle. Okay, so what's this probability here? See if you can figure that out here. I'll walk around a little bit. Figure out what that area is there. What's the width of the rectangle? What's the height of the rectangle? So yeah, Ta, what is the width of this rectangle? It's 9. Yeah, 24 minus 15. Yeah. Okay. And Lucy, what's the height of this rectangle? Yeah, it was still 1/24th. That's right. Yeah. Okay, so what's the area of the rectangle? 9 over 24 here. And 3 goes into both of these. So 3 and 8. So there's a probability of 3/8 that the baby smiles for more than 15 seconds here. Okay, so there's a couple of different ways in which you can look at this. You can look at it in terms of the area, the width of the rectangle and the height of the rectangle, or if you label things with A, B, C, and D, you can just remember our formula here. Either way, you'll get the same numbers. Okay, so do this one here. Either by using A, B, C, and D, or by thinking it in terms of the rectangle, height and width. Yeah, slide 10 right now. Oh, that's not what I want. Okay. So about a 1 in 12 chance.
Yeah.
Baby smiles between 10 and 12 seconds. Okay. And maybe you saw that using our formula here. Maybe you recognize the height of the rectangle is 1/24th and the width is 2. Yeah. All righty. So this just brings it home here that our formula here involves this function for the height and this value here for the width. And if I multiply this times this, I get D minus C over B minus A. A student who's driving home from Ames Community College waits at the traffic light at 10th Street and let's say 59th Avenue. Assume that the wait time is uniformly distributed between 0 and 120 seconds. If that's the case, what's the average wait time? What's the minimum and what's the maximum? Well, what's the minimum and the maximum here? The whole thing. 0 and 120. So What's the average? We don't need our calculators for that. 60. Yeah. Better said 0 minutes, 2 minutes. The average would be 1 minute. So yeah, 60 would be our average. And what's the probability that the student will have to wait between 45 and 75 seconds? Okay, so let's see, that's 30, that's 45, that's 90, that's going to be 70. Okay, so it's somewhere in here. Okay.
So 60 is that me or average?
Yes,
Oh, it's the same.
yes. Much love when people say that. This or that, yes. So 60 seconds. So how do I calculate the probability that the student's going to have to wait somewhere between 45 seconds and 1 minute 15 seconds? 5 minus 45, good. And yeah, that's 30.
One.
Yeah, there you go. This is 1 over 120 here. Yep, 30 over 120, which is a 1 in 4 chance. How's that going? Alrighty, dighty. Okay, good. Ooh, what would be the 75th percentile of the wait time? 75th percentile. Am I going to be slicing it somewhere on the left or on the right? The right, yeah, in such a way that how much area is to the left when I'm slicing it here? How much area is to the left if it's the 75th percentile here? What was it?
75.
75%. Oh, okay. Well, let's write this down here. Let's see. We've got 0 and 120. So that tells me that from here to here,
So
this has got to be 75% of 120. What's 75% of 120? How do I find that out? Yeah, 120 times 0.75, which is 90. So this is 75, or sometimes seated, abbreviated this way. P sub 75 is equal to 90 seconds. And how did we figure that out? So if I'm given a different percentile, just P, how would I figure that out? I mean, you did it yourself. 75% of this full distance here. Okay. And just for grins here, just in case this isn't 0, got to add this on here. So let me, well, that's plus. So yeah, That's our formula for percentiles here. So let me label this as X sub 75 here. So what would be the 80th percentile? How do I find that out?
124 with 0.80.
0 plus 80% is a decimal times 120 minus 0. Yeah. A lot of zeros in there. Makes it a lot easier here. So 4 times 24 is 96. Is that right? Yeah, that's right. Okay. Okay. Now, a conditional probability. Haha. What is the probability that the student will have to wait more than 15 more seconds, given that you've already waited 45 seconds? Oh, what? Let's see. Let's write this out here. So, I mean, this is 0 and this is 120. That means in the middle, I've got 60. Over here, I'll cut that in half and get 30. I'll cut this in half and get 90. And then each one of these is 15 seconds here. So that's 75, and that's 105 here. Okay. So each one of those little sections is 15 seconds there. Okay. What is the, let's see, wait more than 15 more seconds? I'm not sure how to parse that yet, given that he's already waited 45 seconds. Okay, so already waited 45 seconds. We're already dealing with this here. Already waited 45 seconds. Have to wait more than 15 more seconds. Oh, for a total of what?
So I think this 40 is in.
Is 60. Yeah. Okay, so we've got two different rectangles we're dealing with here.
So if it's 45, how come should I be the left side? Starting 0.
Given that he's already waited 45 seconds. So is he going to wait 30 seconds?
Mm-mm.
No. So we're only dealing with the stuff that's bigger than 45.
Mm.
Yeah. So this is a conditional probability. And as you recall, that's notated this way here. Given that he's already waited 45 seconds. So let's call this we've already waited 45 seconds. So our total wait's going to be at least 45 seconds. And if we wait more than 15 more seconds, then what's our total wait going to be? Again, Ta. 60. So let me rewrite that a little
Is that more than 50 or more than 50?
Yeah, what's the probability that somebody's total wait will be more than 60 seconds, given that they've already waited 45 seconds? Sorry? Does that make sense? Yeah.
In the question, is that saying more than 15 or 50?
This is 45.
Uh,
It's not 15 and it's not 50. I'm not sure where you're getting 15 and 50. Oh, 15 more. 15 more than what?
all 15 more than 45. Oh, okay.
There you go. Yeah. So what's our formula here for conditional probabilities? Probability of A given B is equal to the probability of A and B over the probability of B. Okay, so for us, that means that this is equal to the probability that x is greater than 60 and x is greater than 45. Well, that's a little lame. We should be able to simplify that pretty easily. And that's all over the probability that x is greater than 45. Okay. So, x is greater than 60 and x is greater than 45. If something's greater than 60, is it also greater than 45? Yeah. So, for both of those things to be true, what's an easier way of saying that? Greater than 60. We don't really need the greater than 45, do we? So, that's probability that x is greater than 60 divided by probability that x is greater than 45. Can you find those two probabilities? Oh, yeah. It's two rectangles. What's the rectangle on top?
From 45 to 60.
On top,
Oh, on the top greater than 60.
greater than 60. So, yeah, what's the width of that rectangle?
1 minus 60.
120 minus 60,
Which is 60.
which is 60, over 120 minus 0, which is 120. Okay. How about the bottom? What's the width of the rectangle? What's the width of the rectangle here?
But it's greater than
Yeah, going from here to here. What's that width?
45. 75.
75 out of what?
120.
120. Now I've got an over 120 up here, and I've got an over 120 down here, don't I? I've got these two things here. What's a way in which I can simplify this? Can I multiply something top and bottom here to 120? And that's going to make both of those denominators disappear. So I'll just have 60 on top and 75 on the bottom here. And ooh, 5 goes into both of these things. That's 12 and 15. And 3 goes into both of those things. That's 4/5. So that's 80%. Okay, so 80%. So interpret that for me. Yeah, yeah. Another way of saying it, if you are driving with a friend who's notoriously gets upset when he has to wait for longer than a minute for something, and you've already had to wait 45 seconds at this light, what's the probability your friend's going to get upset? 80%. See that? Okay. Kind of brings it to the forefront a little bit there. Okay. So, all right. Yeah, let's do this. Let's do this here. I'd like you to go to random.org. Just pull that up on your phone or on your laptop or something. Um, and you'll see this little dialog box in the upper right here. We're basically just going to generate 100 random numbers. And then I'm going to have you analyze those with your spreadsheet. See what you got. Wonder if I can use my phone. Pull it up there too. So yeah, random.org is a nice it's a nice website in that it really generates um, some true random numbers here. If you really need to generate some numbers that you know are random, you can do this. I mean, I think it actually looks at like sunspot activity or something to see whether or not, to be able to calculate these things here. So it does a pretty good job. So if you want to generate a random number between 1 and 100, some random integer, there we go. So what I'd like you to do is just do this like 100 times. And then for each one of your numbers, just record that in each of these boxes. All right. Like, how exciting. What kind of a distribution are we drawing from here? Is there anything that, is there any preference that it's giving to any number between 1 and 100? Or the probability is pretty much the same? You're right, Boosie. They're the same, aren't they? So what kind of a distribution is this?
I just
It's
keep
random. It's
generating.
always random, but it's
I
from,
keep just generating and then record the number
yep, yep.
here.
What's the nature of the distribution though that we're drawing from? What kind of a distribution? It's a uniform distribution. Yeah. That was fun for me. They'll let me do this here. I can't navigate both of these things here, unfortunately. But yeah, go ahead and make use of that site to draw those things in. Cool. So once you've got your 100 numbers there, go ahead and put those into the column in your descriptive sheet on your spreadsheet. And we're going to be calculating these statistics from your spreadsheet here. You want to get the mean and the median, first quartile, third quartile, and standard deviation. See what we get there.
I just have to put the numbers here, right?
Mm-hmm. So this is very boring.
And then put them in order, right?
No,
That doesn't matter.
nope, doesn't matter. Yeah, and if you're watching on the recording here, hopefully you're doing the same thing here where you're coming up with those 100 numbers, placing them into your Project 2 spreadsheet. Yeah, Boosie, what'd you get for a mean? 48. Yeah. How about Utah? Eventually you'll get them all in there. Sally, what'd you get?
I don't, I'm still working on the first and third quartile. I don't know.
Oh, okay.
Okay.
Yeah. 47.7. Sounds good.
I got 50 for median.
50 for a median.
Mhm.
Okay. Lucy, what'd you get? 46. How about Utah for the median? 45. Interesting. First quartile? Let's hear those. 29. Okay.
Me to 29.
Oh, as well. 29 for first
25.
quartile?
29.5.
29.5. And 17.5. Okay. How about the third quartile?
69.5.
69.5.
66.
60. Interesting. 72.5. Okay. All of them, all three of them kind of low. How about the standard deviation?
Mhm. Where did I get them? Still
Let's just do two for this. 26.78,
28.64.
28.64, 30.72. So are these things exactly the same? Nope. Are they pretty close? You
Yes.
can kind of see what's and in fact, if we were considering this theoretically using classical physics, classical probability, what should the mean be? 50. And also, what should the median be? Also 50. Yeah. What should the first quartile be? 25. And the third quartile?
So
75. Okay. We could actually figure out what the variance or the standard deviation would be. I think it's 100 squared over 12. So these two things cancel. It's 100 over the square root of 12. I don't know what that is.
is that 100%?
Just the difference between A and B. That's in the formula, actually. Yeah. So yeah, 100 divided by the square root of 12. What was that? 28.86. Is that pretty close to kind of things you all came up with? Yeah, it's pretty close here. Do you think these things would get closer if we pulled out 500 values, 1,000 values? Yeah. The law of large numbers, once again, as we increase the sample size, empirical probability gets closer to classical probability. Okay. Also, what do your histograms look like when you're doing this here? And specifically choose 8 bars. Yes, I'm looking at TAWs here for, make it 8 bars. So you're going to choose the number of classes up near the top.
Oh, okay. But I have to change the
It's
number.
one of your green boxes there. Number of classes.
This one, right?
Yep.
How many should I put? Like 100?
Let's try 8 first. Okay, that looks interesting. Huh. And yours looks different there. Okay, so actually, could you switch yours to 5? So yeah, Lucy, what'd you get there? Interesting. Yeah, you had something that's kind of similar to that. Okay, so this is 8 bars here. For 5 bars from Ta, actually kind of smooths out a little bit because there's more numbers in each bar. So things kind of smooth out, don't they? But theoretically, what should they be? It's from a uniform distribution. Uniform, exactly. That's right. Okay, so uh, we've covered this. This is what the theoretical values were. Um, and so let's compare theory to experiment here by constructing a couple of box plots here. So let's do a scale down here that goes from 0 all the way out to 100. And let's divide this up 50, 25, 75. And let's create 2 box plots here. Experiment and theory. So what would our box plot look like for theory? The median is here at 50, isn't it?
Mhm.
The first quartile's at 25, and the third quartile's at 75. And the min and max should be basically here to here. Should look like that. For experiment, mark these things where yours were. Be slightly different. Gesundheit. So your answers are all going to be different for that second box plot there. But see how things line up or don't line up. Okay. So whatever yours looks like, you can see that it has a resemblance to theory, but not exactly lining up. Okay. And if we were to increase the number of random numbers here, would these things line up more or less? More. Yeah. Okay. So that's chapter five. That's all of chapter five here. And so if you take a look at the assignments for this, there's two assignments, one for the first section, the other for the second section. Okay, so continuous probability distributions. So there's not a whole lot to this here. I mean, I kind of created this, kind of silly thing right here. Um, if you're taking a look at this enormous distribution here, it extends from x equals 0 to x equals 12. So answer the following questions. What's the area under the entire distribution? 1. Probability that x equals something? 0. Probability that x is somewhere between 0 and 12?
12? No.
Yeah, it's got to be somewhere between 0 and 1, right? Probabilities are somewhere between 0 and 1. But what's the probability that x is somewhere between 0 and 12? 1. That's the whole thing, right? That's the whole thing. So what's the probability that x is 12? X is 12, less than 12, I should say. Same thing. What's the probability that it's bigger than 0? Also 1. What's the probability it's greater than 12? 0. That's off the chart there, isn't it? Yeah. How about less than 0?
0.
0. See how that works? It says a lot of things, even knowing very little about the distribution, you can make a lot of statements based upon what you see here. Okay, so
Where's
you're,
the homework for today?
did I not? I might need to unhide it.
Letter? Oh,
So, and if you're told that 40% of the area is to the left of x equals 4, you should be able to figure out the rest of these things here and so on and so forth. So you've got some independent practice here. Given the uniform distribution below, find the probability of the shaded region. What is it? 2 over 9. Looks like y'all are getting this. And how would we say this? The probability associated with this shaded area right in here.
the last one?
The last one. That's right. Between 6 and 7. Yeah. Okay. So that's the kind of thing that you've got here for the first one. And for the second one, these are specific to uniform probability distributions. Maybe some of these formulas look a little bit familiar here in the guided practice section. The time it takes a person to wash the dishes is uniformly distributed between 11 minutes and 16 minutes. What's the probability that a randomly selected event of washing dishes will take a person between 13 and 14 minutes? Yeah, you've just got a rectangle inside of a rectangle there that you'll draw out and figure out. 1 over, looks like 1 over 5. Yeah. Yeah, I can understand why you think 16. This actually starts at 11, doesn't start at 0.
Okay.
So the width here is just
Okay,
5.
so
Yeah. Same idea here. Okay, if our distribution goes from 0 to 2, what's the probability that we're somewhere between 0.74 and 1.26? It's 2 rectangles again. So that's essentially what we're dealing with each one of these problems here. The value of a stock varies each day from this to this with a uniform distribution. Find the third quartile. So 75% of the time the stock is below what value, or yeah, is below what value. Okay. So that's those two things. Let me actually also take you through a process here of adding something to your spreadsheets that you're going to be needing as we get into chapters 6 and 7 and beyond. So I'd like for you to take a moment here and pull up your statistical tools here, your spreadsheet. And what I'd like you to do is you're going to be creating something that looks like this. And I'm going to take you step by step on how to create that. Hmm? So first thing I'm going to have you do is to click on the plus sign in the lower left-hand corner. We're going to be creating another sheet here. And it shows up here as sheet 33 for me. It'll show up something different for you. But I'm going to double click on this to change its name. And let's call it Z and T scores. Z and T scores. Okay. And let's go through the process here. Let's click into A1 and let's type Z scores. Let me zoom in here. And under G1, let's type in T scores. And let's just make it so this whole row here is boldface and 18-point font. Okay, 18. Okay, and then let's go down to B3, and we're going to type enter Z-score under B3, and then down to B7, and let's type enter P-score. And let's make both of those boldface. And then below that, let's make this cell below each one of those things nice and green, our usual green color for indicating this is a place where you can change, where you can input something. Okay. And then over here, let's type probability that little z is less than big Z. And to the right of that, let's type probability that little z is bigger than big Z. And let's make both of those boldface. And then here in C4, let's type one tail. And below that, let's type two tails. Okay, and let's select both of these. Let's make them boldface, and then let's also right justify them here. That comes from clicking up here and choosing this. Okay, so that'll be nice there. So they should move to the right like that. Let's select all four of these cells here, and let's make it so that we are choosing a border style. Yeah, let's go ahead and choose the large thick lines here. And then let's choose all borders. Ooh, that's too much. Let's make it so that it's like that. That's the middle of the three options there. All right, and then under D7, let's put 4 Z-score, and that's boldface. And underneath it, we'll highlight the borders there. Okay. Then let's also shrink this A column here. We don't need that to be so wide. So I go up here and I can, if you see the two lines here that form, if I click and drag my mouse, I can shrink the width of that column there a little bit. Let's move to the right here a little bit. And then under H3, enter T-score and DF. Little d, little f. And to the left-hand side, this will be T-score. And then below that, little d, little f. It stands for degrees of freedom. Let's make this boldface. Let's make these two things boldface and right justified. And let's highlight both of these cells here and label them as input cells. Okay. Then down here, I've gone down to H7, and I've got enter P score and DF. And on the left-hand side, you guessed it, P score and DF. And I'll make this boldface up here. I'll make these two boldface and right justified. And then I will color these two cells in green. While I'm at it, I can take column G here and shrink it just like I did column A. Okay. And so to the right here, we're going to have something very similar to before here. One tail, two tails. And up top, I'm going to have probability that little t is less than big T. And then probability that little t is greater than big T. I'll boldface both of these. And I will boldface both of these and right justify them. And then down here for T-score. So that's in J7, J7 for T-score. And then in here, I'm just going to create the borders there. Create borders around this singular cell there. All All right, so you should have something that kind of looks like this. Okay, so all the formatting is done here. For a z-score, let's just put in 0 here. And a p-score, let's put in 0.5. And while we're at it here for a t-score, let's also put in 0. And for df, let's put in 10. P-score, let's put in 0.5. And let's also put in 10 for those. Some test values there. Okay, some nasty formulas and then we're done. So here's the first nasty formula. It's going to go under uh, D4 here. And it looks like this. Equals norm dot dist. Norm dot dist.
Do I autofill for the tails?
No, no autofill. Okay, we good there? Okay. This one to the right. That one's a lot easier. It's 1 minus that. It's almost like these two things are complementary events. Ready? Let's go to the front again here. And here's the formula for this. This one's a little yucky.
Which formula is this one?
Oh, yeah.
I don't see which formula is gonna be. The two tail?
What's that? Yeah,
The
this is for the two-tail one on the left.
oh,
Two-tail on the left. Oh, that's good. Lucy's good. All right, Sally's good. All right. So let's move to the right here. Let's take a look at this one. It's very similar to the previous one. Cool. All righty. And then for the z-score one down here, that one's a little easier. Norm INV, and it's got 3 parameters. Okay, so now I'm going to zoom out here a little bit because this is what you should have now. If I put in 0 for z, you should get 0.5s and zeros up here. And if I put in 0.5 down here, I should get a 0 for z here as well. If I put in a 0.95 in here, it should be like 1.64485. And if I put in 1.96 for this here, it should be like 0.975 and 0.04299 for the top one tail things here. Looks like it's functioning. We getting that? All right, very good. Let's do the same thing here now for the t-scores. So let me zoom in here. That's what goes in the upper left here. Okay. And then for the one to the right, yeah, that's the easy one. And so what should the numbers in the two top boxes add up to? One. That's right. Always, always, always. Yeah. And then this one down here, yeah, this is going to be another one of those. Okay. Then the one to the right of it is going to be very similar. You should have very similar numbers in these boxes, what you had before. It should be 0.5s and zeros. And then this one here is our last formula. Alrighty, so if we look at what we've got here now, yeah, that's what those should be. Let's see here. I don't I don't really know any specific ones here. Let's just do that. See what we get here. With 11 degrees of freedom, 0.962 and 0.0379. Yeah, 0.975 here. This should be 1.9989. Excuse me. That's it. We're going to be using these a lot in class as we're learning about the normal distribution and eventually the t-distribution. So very, very cool. Glad you've got that. Now that's part of project 4 that you've actually just finished. Um, and the only other parts of project 4 that you would need to complete would be the binomial distribution part here. Please make sure that you have that done because it gets a lot easier to do the test if you've got this spreadsheet here. And then also, you're going to be creating a bunch of normal distributions, like this, and see some of them will be, overlapping, and some of them, not overlapping so much. So you're going to be seeing how those things work out. All right. So it's those two things. That's part of project 4 there. Let's come back to where we're at here. So you can see that in addition to assignments 5-2, and it should be up there. I'm not sure why you're not seeing it. Let's do the 8th.
Oh, I was expecting to do it today. That's why I was like,
You can also do it today if you want to do that. That's right.
I'm like,
So
there's no homework.
that's right. So
Okay.
yeah. And then project 4 is due on the 8th there. And so I want to have that done so that you're ready for tests 4 and 5 there. Let me just end up by handing back at least chapters 1 and 2, the test there. And back test 3 yet, because not everybody's taken it. You go, Bussy. Oh, why am I not seeing your test? Your first test. Yeah.
Is that for the unit 2?
Yeah, 1 and 2.
I think. I think so.
Oh, already?
Yeah.
Oh, you got, oh, gotcha. I feel better. Okay. Yeah, we're in the.
I'm only for the last one.
Uh,
Yeah, I think I'm only for the last one.
right. Okay, let's go over this test here real quick. Then I'll let y'all go. So yeah, a survey was done asking 300 students their ages. A table was produced to display the results of the survey. So we're not thinking at all about the population yet. So this is descriptive. We're not inferring anything. So we're only looking at the M&Ms that are in your hand. Okay, so key term with each item listed below. Let me zoom out so you can see this here a little better. So the best connection to statistic here is the average recovery time of the randomly selected group of patients who had a heart attack. So this is the sample right in here. Um, for B, the best matching for data here, the recovery time of one person who had a heart attack. That would be an example of some of the data here. This is the parameter, so we're looking at the population. That's the average recovery time of all people who have heart attacks. That's the key there is all. Um, F is the recovery time. That's the variable involved with this. A group of patients who have had heart attacks randomly selected. That's the sample. And all patients who have had heart attacks. That's the population. It's kind of a vocabulary check there on all those. Number of doctor visits in the last year. Well, it's quantitative, but we can't have a half of a doctor visit. So this is quantitative discrete. Sampling method where you divide the population into different groups and randomly select a sample from each group that's stratified. That's where we go. I want 3 ninth graders in my sample. I want three 10th graders I want, three juniors, three seniors. Yeah, stratified sample. Suppose we begin with a complete list of schools that had students take the AP Stats exam last year in Minnesota. 5 of the schools are randomly selected from the list of all schools. So we're choosing to cluster our sample to just these 5 schools here. That's a cluster sample. Convenience sampling can be used to construct a representative sample. The answer is false. Convenience samples don't do that. Here's the table results here. If you got the frequency incorrect, then I recalculated your stuff to the right there to make sure that, if you did this right, even though this was wrong, then I marked this right because the math was you're still mathing correctly. Question 9, yeah. The key here is 1 to 4 is 14, so this is 56. That's the largest, most expensive item sold there. This is symmetrical, so the mean and the median will be about the same. Yeah, top one is symmetric. C is bimodal. Most common error was switching these two here. So skewed right would be this. So the right side tail is more noticeable than the left side. And this one is skewed left down here. Yeah, these two are the hardest problems right here. So this is a frequency table here. So you had to use some special formulas in order to be able to do this in order to find your mean, median, and mode here. How many people are being represented here? This is 9 plus 2 is 11, 13, 14, 15, 16. Okay, so if we're taking a look at the median, well, there's going to be 9 zeros before we get to anything else. And half of 16 is 8. So we're going to be in between the 8th and the 9th value, both of which are 0. So the median is going to be 0. And the most common value is the mode. That's also 0. The mean, what we'd have to do is add 9 zeros to 2 ones we can ignore that, to 2 threes, to 1 4, to 2 fives. So oftentimes what we do is we multiply these things and then add them and take it from there. You get 1.4 when you do that. All right. If you put these into your spreadsheet, you'd get this for a mean and this for a standard deviation and this for a variance. You'd have to use a formula in order to do population standard deviation. That was just 2 points at the bottom there. That's it. Questions on that? Any other comments or questions for the good of the order? Okay. Have a great 4th of July weekend, everybody. I will see you next week
Let's enjoy.
on Tuesday. Yeah.